Have you ever looked up at the night sky and just felt completely overwhelmed by the sheer, quiet vastness of it all? The silence of the universe is haunting, isn't it? But beneath that silence, there's actually a massive, multi-agency scientific endeavor actively hunting for whispers in the dark. Welcome to our explainer today. Are we alone? The cosmic detective story.
Are we truly alone? It's the ultimate mystery, right? And this single question has completely transformed the search for extraterrestrial life. We're no longer just dabbling in philosophical speculation. No, this has become a high-precision, data-driven hunt. We're analyzing, calculating, and deploying the absolute most advanced tools in human history to literally scan the cosmos.
And to solve a mystery of this magnitude, we really have to think like investigators. There's a famous quote from Sherlock Holmes that NASA actually included in their own independent report on unidentified anomalous phenomena. It goes, "Once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth." That perfectly sets the forensic tone we need, because astrobiology is fundamentally about ruthlessly eliminating the impossible until we are left with the undeniable truth.
Part 1. Mars Potential Biosignatures. Let's head over to our planetary neighbor and see how this investigation unfolds.
The Curiosity rover has been playing the role of a cosmic detective since 2012. We used to just look for dried-up riverbeds to see if Mars was ever habitable. But recently, scientists did something far more thrilling. Down in the Glen Torridon region of Gale Crater, they deployed a highly specialized solvent called TMAH. Its job? To ruthlessly break apart complex organics locked deep inside 3.5 billion-year-old Martian mudstones. These rocks have been sitting there undisturbed for billions of years. And the results? Honestly, they were stunning.
They detected these very specific long-chain carbon molecules, things like decane, undecane, and dodecane. Why does that matter? Well, on Earth, these specific 10, 11, and 12 carbon chains are the literal building blocks of cellular membranes. They even found complex double-ringed sulfur molecules and nitrogen-bearing structures that look awfully similar to the precursors of DNA.
Here's the truly wild part. Non-biological or abiotic processes just can't fully explain these specific patterns. Natural events like lightning strikes, hydrothermal vents, or even passing meteorites really struggle to account for the exact chain lengths and the sheer abundance of these molecules. So what does that leave us with? Tantalizing potential biosignatures on the red planet. Now, to be clear, it's not definitive proof of ancient microbes yet, but man, it is a massive, glowing clue.
Part 2. The search is new science. Let's look at how our methods are evolving.
As this forensic journey gets deeper, scientists are realizing something crucial. Simply finding individual organic molecules just isn't enough anymore, because space is absolutely full of random chemistry. We need a way to tell the difference between a lucky chemical accident and the deliberate engine of biology. So we're shifting away from hunting for single silver bullet chemicals. Instead, we're looking for statistical patterns of organization, a framework called ecodiversity. Basically, life doesn't just make molecules, it organizes them.
We can actually see this organizational fingerprint clearly in amino acids. Living biological systems produce a high diversity and a remarkably even distribution of these molecules. But if you look at a lifeless meteorite, the chemistry is skewed, random, and much less diverse. Life literally leaves a mathematical signature behind.
On the flip side, with fatty acids, life produces a less diverse, highly specific pattern based exactly on what an organism needs to survive. And this statistical signature is incredibly robust. Scientists have tested this and found that these biological patterns survive even in heavily degraded samples, like fossilized dinosaur eggs. Seriously, how cool, Sat? It's an absolute game changer for astrobiology. And this exact statistical framework is going to be absolutely vital for future missions, like NASA's Europa Clipper. Arriving at Jupiter in 2030, this spacecraft will literally fly through plumes of ice erupting from Europa's hidden subsurface ocean. It's going to use its surface dust analyzer to look for these exact mathematical ratios in single grains of ice. We might actually find out if an alien ocean is harboring life right now. Part 3. UAPs, the unknown skies. Now, let's bring this search a little closer to home.
Because exploring the unknown isn't just about looking millions of miles away. It's also about scrutinizing anomalies right here in our own atmosphere. Take a look at these unidentified anomalous phenomena captured by advanced military sensors. Now, NASA's independent study team is very clear. There is zero proof of extraterrestrial origins here. But these visual anomalies demand the exact same rigorous, transparent, scientific investigation as those rocks on Mars. The stigma is finally fading, and serious data collection is taking over.
To actually figure out what these things are, scientists are constantly stressing the need for hard, calibrated sensor data. Eyewitness accounts are super compelling, sure, but they aren't reproducible science. As NASA points out, we need to train advanced AI and machine learning networks on a massive baseline of normal aerial data. Only then can the AI accurately flag what is truly abnormal.
Official government investigations show that most UAPs do resolve to ordinary things. Balloons, birds, optical illusions. But here's the kicker. Unremarkable doesn't necessarily mean identified. There are unresolved cases featuring actual physical objects that lack the performance data needed to easily explain them. We have to systematically strip away the mundane to find the things that truly challenge our understanding of physics.
Part 4. The big question. Let's pull all of this together.
When we synthesize the discoveries on Mars, the breakthroughs in chemical organization, and the atmospheric anomalies on Earth, what does it all suggest? Well, first, we absolutely have to separate fact from fiction. You've probably seen those sensational claims, like the supposed alien mummies in Mexico, which were quickly debunked by DNA analysis as just modern assemblies of animal bones. Or those interstellar spherules, where the seismic signal actually turned out to be a passing truck. Yikes! True discovery requires reproducible data, multiple lines of evidence, and rigorous peer review. No shortcuts.
But the real, rigorous science is accelerating at breakneck speed. Tools like the James Webb Space Telescope are pushing our boundaries to new limits. We're now characterizing distant exoplanet atmospheres, like the potential ocean world K2-18b, looking for disequilibrium gases. Basically, we're looking for gases that just shouldn't exist together unless something biological is actively producing them. Definitively proving life is still just over the horizon, but we are getting so close.
Part 5. Not the only observers. Let's take a quick step back and look at the big picture.
Humanity has this relentless, beautiful drive to look into the stars and figure out where we fit into all of this. Seeing Earth viewed against the haunting silence of the cosmos really drives home our fragile place in this vast universe. But you know what? That silence is no longer empty. We are actively listening, sampling, calculating. The grand journey of cosmic discovery is already well underway, and it's happening right now.
The scientific net is cast wider and deeper than at any point in human history. So I'm going to leave you with this final, lingering thought to ponder the next time you look up into the dark. What if we are not the only observers in the universe?